This is our ME372 final project video. I'm Carson.
I'm
I'm
Brian
Ryan
Merritt.
Tanner.
I'm Justin Ward.
And we are going to present our project.
Okay, so the project was to create a jack that would be loaded in tension, and it was supposed to support a maximum tensile load of 2,000 pounds. It was designed for like farm workers and construction workers, so it's going to be used pretty frequently. And it was supposed to raise and lower only 6 inches, and we used a lead screw for that. We also wanted to account for appropriate safety factors, so like around 2 to 2.5. And like I said, it would be used a lot by construction workers. So we figured that the max amount of cycles that it would go through would be about 5,000 cycles. So we used that in our fatigue approach. We wanted it to be easy to manufacture with common materials. 1018 steel, for example, was the most common that we used. And we wanted it to be simple design. And we wanted it to be relatively light, but also able to endure a lot of load. And we also decided to coat the design so that it wouldn't, so that it'd hold up under the elements. And we designed it so that it would fail in a non-catastrophic manner. And next slide. Okay, so in order to prevent failure, we wanted to load it beyond, to prevent failure, you should not load it beyond 2,000 pounds. Don't load at a non-vertical angle. And if you go beyond, it's not designed to go beyond the 6-inch range of height. And we started that at 8.2 inches and it raises to 14.2 inches. And we also just counsel to avoid notch sensitivities like chipping and stuff so that it can hold up under pressure.
So the way we approached our design was we decided to use Excel so we can take more of an iterative approach. This would allow us to use like user input values for our parameters. So they didn't come with the program. We entered all these to get our values. We wanted to ensure that all of the members did not fail below 2,000 pounds. And we wanted to allow for more than that if possible, just in case it was loaded a little higher than 2,000 pounds. And we also iterated to reduce the factor of safety. This was also to reduce the cost and weight. For material selection, we decided to go with 1018 steel. This table shows the material properties for steel. The Young's modulus wasn't needed for all of the different parts of the design due to not all the parts being under compression. Since only the crossbar was under compression, we needed the Young's modulus for that. We had the yield strength for all of them, and then the ultimate tensile strength, the crossbar and the diagonals were the main focus for that, since those would be under the most fatigue.
All right, and so then for our model, like you can see in the figure before on the previous slide, there were many different places that we wanted to check for failure. Our biggest focuses were buckling the crossbar, axial failure in the diagonals, as well as pure shear in the side pins, but we did more than just that, just to ensure that there was no other place that we were missing. And then we designed it so that the first place to fail would be in buckling. And as you can see in the model, at the minimum height, the buckling and the crossbar will be able to handle 2,000 pounds, just over 2,000 pounds, before that buckling occurs. Also what we did, as can be seen from this table, and then on the next slide there'll also be more images, that we did a FEA analysis with ANSYS on the diagonals to determine what the loads that they would be under were, just to make sure that those would have no chance of failure, because we determined that the failure in the diagonals would be catastrophic. So upon doing that ANSYS model, we were able to see that the load that the diagonals would undergo would be roughly 4,000 pounds when it's at its minimum height, and then about 2,300 pounds when it was at its maximum height. But then because of the material choice that we made with the diagonals, we just had beam steel. Like Justin said, the failure loads limit at its minimum height and at its maximum height is well beyond what it's actually experiencing. And so that can be seen in this table, and then like can be seen in these images. This is just the images that show it. So the top picture is the jack when the 2,000 pound load is applied when it's at its minimum height. As can be seen, that stress is down at the bottom there on the side that is probed is 9,118, and the same thing goes with the bottom one. It is lower when it's at its maximum height, and then the table before just converted those into a load, which is what, and from this we can see that the diagonals will be able to successfully handle the weight with the steel choice.
This plot's showing the failure load for each member of the scissor jack as a function of the height range between 8.2 and 14.2 inches. So the main takeaway from this is that all of the failure loads are above 2,000 pounds, which is one of the critical design requirements. So for all loads applied below that threshold of 2,000, it is safe, and no part in the system will fail at all. And here, again, as a function of height, we can see the safety factors. We tried to, as mentioned earlier, we tried to minimize the safety factors in order to avoid over-designing, which would increase cost and issues like that, while maintaining safe factors of safety to prevent failure as much as possible. Ideally, we would want the crossbar to buckle before anything else, because we deem that to be not catastrophic, meaning that if that broke, the system would still be intact, so that the load would not fall from it, which might happen if something more catastrophic happened, for example, the side pins shearing or something like that, which is why you can see here the crossbar buckling is one of the lower, has one of the lower safety factors, and also things like bearing stresses also have lower safety factors, because again, they are not as catastrophic as something like the axial stress causing breakage in the frame, which has a much higher safety factor, as you can see towards the top of that plot.
So then overall, we just recommend that this jack be made out of 1018 steel for the majority of the parts, that meaning the diagonals and the crossbar. This will cause a slightly increased weight to the jack versus if we would have decided to use a different material such as aluminum in the diagonals. However, we decided this because it will allow the jack to successfully handle the loads that it will be subject to, and it will limit the possibility of failure.
Yeah, one thing also about a good thing about making everything out of, or the bulk of the materials at least out of 1018 steel, is that by not having so much variance in the type of materials used, from a manufacturing perspective, we're also reducing costs just by homogenizing all materials used and things like that. It just kind of brings costs down.
We can pretty confidently say that our design will be able to handle a 2,000 pound load in suspension in tension at its maximum and minimum height. We did this, I mean, as you could see in the results, most of the parts were able to handle even more than 2,000 pounds safely, to allow for extra weight, just in case the user did exceed 2,000 pounds.
And so once again, yeah, we did not design this for compression, so we're not sure what loads this can handle in compression. So we just recommend against not loading it in compression. Thanks for watching our presentation. Any questions?
No? All right.